Hello, this is Jack Jackson. We're going to be looking today at the derivative at a point, derivative of a function at a point. And so we're going to look at this graphically in this particular video, and we're going to be using a GeoGebra file that I created for this. So if you look at this graph that you see here, the graph in purple is the graph of our function f of x, and at the moment I have this set as the function 1/20th times x minus 6 times x plus 4. So we have this nice little cubic polynomial function graphed in purple. Now what we're going to do is we're going to take this and we're going to select a point on this curve by selecting a value for a. And I'm going to move this over. I'm going to select a to be 4 to start with. And I can pick several values for a by using the little slider here in blue. And notice that the value of a is 4 shows up here in cell B2 in the table. Now, then we can plug that value of 4 in place of x and work out what this is. You know, like for example, 4 plus 4 is 16, 4 minus 6 is negative 2, and x is 4, so we got 4 times negative 2 times 16 and divide by 20, and at least approximately that works out to negative 3.2. So you see the point 4, negative 3.2, is our point a, f of a, which is this blue point on the graph. So far we're doing nothing more than just evaluating the function. Now what I want to do is go to a nearby point, and I can control this value h by this slider. For the moment I'm just going to leave it where it is, where h is 1, and as I change that value of h, it'll show up over here in the table, so h is 1. So what I want to do is I want to add h to a. So we're going to look at that. So if you add a and h, that gives you the point 5. So that's going to give me our point, our x value, which I'm going to call t, which is a plus h. And so that gives us this point right here that you can see on the graph, on the axis. Now if we then do f of that, in other words, take that value, so let's see what it is. 4 plus 1 is 5. So take that value of a plus h, or t, and plug it in place of x up here. So we're doing f of t, that is f of a plus h, or in our case at the moment that's f of 5. So we're plugging 5 in this formula for x and working it out, and approximately, at least, that turns out to be negative 2.25. So that means this point right here is the point 5 comma negative 2.25 is another point on the curve. Now what we want to do is take those 2 points and find the slope between those 2 points. That is the slope of this green secant line here. And of course all we need to do is find delta y divided by delta x. Delta, Greek letter, looks kind of like a triangle, stands for difference in or change in. So the difference in the x's, t minus a, is t minus a. So it's this t minus that a. The difference in those two x's, that's sort of x2 minus x1, t minus a. Or since t is a plus h minus a is just h. So h is delta x here. So this red distance that you see right here with this triangle right here, this red side is just h, which is delta x. And that's, of course, that's controlled by the slider. So h is 1. So that's our delta x. Well, what's our delta y? Our change in y's. Well, it's this y minus that y. So that's going to be f of a. I'm sorry, we'll do this point as the second point. F of a plus h minus f of a. So that is the negative 2.25 minus the negative 3.2. Well, if you do negative 2.25 minus a negative 3.2, that's negative 2.25 plus 3.2, which is 0.95. So that's our delta y. We're dividing by h, so dividing by 1. That's 0.95 is the slope of that green line. This is what we call a difference quotient. So let me write this down for you here. So what we're looking at for a difference quotient is nothing more than the slope formula. It's delta y over delta x. Okay? But in our case, what are these things? We can actually look at it two different ways depending on how I notate this. I can just say, well, it's the delta x is the t value, that's x, the second x, minus my initial x of a. But we also see that that is the value h. Okay? And then what we want to do with the y, we want to take the f of t minus the f of the a. Or t is another way to write t is a plus a little bit more plus h, like that. So typically I'm going to write it this way. And so that's what we call the difference quotient. And this is the slope. This is a slope of the tangent line. And the slope of the tangent line, notice it goes through the point we're interested at. We're interested in the blue point, point A, f of A. And we want, and some nearby point, the green point. This is also the average rate of change in the function over that interval. So it's the average rate of change, or the difference quotient. Okay, it's just a slope. So basically something you've been doing since, intermediate algebra, algebra 1, somewhere back there. Okay, now what we want to do now is manipulate this a little bit. So we're going to leave the blue point fixed, so we're not going to move the slider for A, but we're going to take the slider for H. Now what we're interested in finding out is not the slope of the secant line or the average rate of change. We're interested in finding the instantaneous rate of change. So what we want to do is we want to take this H and we're going to slide it a little closer to 0. Now notice the numbers changed a little bit here because this secant line moved. In this case, the slope's a little smaller. Okay? And that should give us a better estimate of the actual instantaneous rate of change. Well, what if we did it a little closer still? Okay? Or closer still. And every time I'm moving this in just a little bit to the where h is getting closer and closer to 0, notice that the slope is changing a little bit. That difference quotient very slowly is changing, and it's getting closer and closer. Now if I ever let it actually hit 0, right there it's 0, notice that the secant line disappeared, and you got a big question mark here in the table where it says what the value of the difference quotient is, because it's undefined, because then you get 0 divided by 0. You actually have to have two different points to be able to use the slope formula. In fact, you have to have 2 points with different x coordinates, so the slope formula doesn't make any sense. But I can make sense of it if I do something close by. But notice that this is getting closer and closer to what? Well, we're getting closer and closer to a tangent line. So the secant line is getting closer and closer to the tangent line. The h value is getting closer and closer to 0. The t value is getting closer and closer to the a value. Okay? And the slope of that secant line is getting closer and closer to the slope of that tangent line. That is, the average rate of change is getting closer and closer to the instantaneous rate of change. Now this idea of letting something get closer and closer and closer to a value and seeing what something else gets closer and closer to is what we call a limit. And the limit is the fundamental idea of calculus. So what we're doing is we're taking a good old basic algebra property, the slope, and we're applying the calculus idea of a limit to this process, and this allows us to find the slope at a single point, that is the slope of the tangent line to the curve, or to find the instantaneous rate of change. The slope at a single point doesn't make sense when you're using just the slope formula and we're talking about pre-calculus. But once we apply the limit, then we can make sense out of the slope at a single point, that is, the instantaneous rate of change. Now, it's also possible to let h be negative. That just means the green point is going to be to the left of the blue point. So this is a full limit, both left-sided limit and right-sided limit. Notice that these values here, look at these values in the table here for the difference quotient right over here in cell C12. There's the slope, there's the difference quotient. And look what happens as we get closer and closer to 0 with h. They're changing. It's about half there. 0.52. What's happening? Okay, it's getting a little bigger. 0.57, 0.58, 0.59, 0.6. Okay, look what's happening. Those values are now they're climbing up. Okay, getting higher. Whoops! Now we're going. I've gone too far. I've gone to the positive side of h. So as h has gone too high, so we come back, getting h closer to 0. What's happening with those values? 0.56, 0.55. Should be getting closer to the actual slope of that tangent line as we get closer and closer to 0. Of course, once again, we cannot let it be 0. Okay, we should be getting pretty close now. 0.44, 0.43, 0.42, 0.41, 0.41, oops, undefined there on this side, about 0.4, 0.39. Look, what does it look like it's getting close to? Maybe 0.4. In fact, it turns out that the slope of the tangent line is actually right here, and it actually is exactly 0.4. Okay, and I can actually show the tangent line. By the way, what's the slope? What's the equation for the secant line? Let's move back over here a little bit. Okay, so here's a pretty big h. Let's do a little bit better than that. There we go. 0.94. 0.91 is the slope of that secant line, and so we can use the point slope form of the line. And the point slope form of the line says y equals, there's your slope, m, 0.91 from the difference quotient, and then parentheses x minus the x point that we know it goes through, the blue point, that's a, x minus 4, and then you say plus the y that it goes through here, which was the y that goes with that point, negative 3.2. Okay, now the actual tangent line, which is kind of what we're interested in, here turns out to be its formula. The slope is actually exactly 0.4. And if I take this and right-click on this, I believe I can say show it, and now it will actually show over here on the picture the tangent line. And again, you notice that this is getting closer and closer to that tangent line as that h gets closer and closer to 0. So that's using that's the introduction to the difference quotient, and then the which is the slope of the secant line, or the average rate of change. Then we take a limit as the h goes to 0, and now we have the slope of the tangent line, which is the derivative. Okay, so that's the derivative of f at a. Now we can, of course, change the value of a. We can change the value of the function in this little applet by changing the value of the function by changing what's in cell B1. We can change the value of a by moving the slider, and of course we've moved the slider for h quite a bit.